Welcome again back to the lecture, especially the lecture on the first module. In the last lecture we have seen few interesting examples, starting with the population growth model, both its linear and nonlinear versions, and then we have seen the atomic waste disposal problem, and finally two problems from fundamentals of mechanical engineering. They use it extensively, the spring mass system and the electrical circuit, simple electrical circuit. What surprisingly we have seen is that both this model leads to the same second order equation with constant coefficients. The another interesting observation from our first two examples is that even after getting solution, especially the population model, getting solutions whether it is in an implicit or explicit form is not sufficient. You have to do more analysis on it, because the solutions in the explicit or implicit form will not reveal much about the physical model. And in the second example, atomic waste disposal problem, we have first modeled it as a linear problem. We have obtained the solution, but it did not resolve the exactly what we wanted to, and then we remodeled it as a nonlinear problem, but the nonlinear problem was difficult. We could solve it and get the equation in a implicit relation. We could not make it an explicit solution, but that was enough for us to conclude that dispellers of the whether we can do it, the question raised by the environmentalist. So, this see that how you model, how you solve it, and even after solving it, doing it in the analysis are very important, and that is the purpose. As I said in the beginning, the purpose of the course is not just to solve it, which normally is difficult, but quite often explicit or implicit solutions are not the important aspects of the theory. It is how do you understand its trajectory and how its behavior and what is the physical demands, and that what we want to do it. Now, what I am going to do it, we will continue with the last two problems, the electrical circuit problem and mechanical thing, and we have obtained the equation and we want to interpret the or rather analyze the equation. So, let me recall the second order equation which we have derived, second order equation. What was the second order equation? M into d square y by dt square plus c into dy by dt plus k into y is equal to f. So, this was the second order very simple equation, linear, and what the other interesting thing is that with constant coefficients. So, you will learn more about this first order second order equation later, but so I am not introducing to you how to solve this equation in this particular lecture. I will write down the solution, and my aim is to give you the interpretation of this equation, where the thing is that where m, c, k, m, c, k are greater than, in fact let me tell you, m and k are greater than 0, then only you have non-trivial mass and thing, and c can also be. So, this is c is the mass which you have. Let me recall mass. This is the spring constant, and this is the damping. So, I want to analyze this equation extensively now and give you an interpretation. So, I will be introducing few notions like that. You will understand why this is. I call it omega naught is equal to square root of k by m. This is called the natural frequency of the system. You will understand why it is called a natural frequency when you analyze it. this is called the natural frequency. So, when you develop a mechanical system, it has natural frequency of the system, you see. So, this we will introduce more and more notion. So, I am going to analyze it case by case. So, we will start with case 1, and this in this case I assume. So, I am going to do it more and more. Assume C equal to 0, that means no damping, and then I am also assuming that F equal to 0, that means this is no force, no external force, no external force. So, this is the situation, free undamped motion, free undamped motion. Then you know immediately this equation. In this case, equation is, what is the equation? M, I will C is equal to 0, F is equal to 0, and divide by M this equation. I can write this equation as d square y by dt square is equal plus omega naught square y equal to 0. This is a simple harmonic type motion, you see, very equation. It's a nice equation. There is no external force, no damping. Then you know that the second law, the first law of motion, Newton's law of motion should obey. Let us see we can interpret that equation. So, okay. So, let me write down the solution. I am not going to tell you, you will learn this when we, as I said, when we study the second order equation. I will just write the solution y t. Those who have learned a course, a preliminary course on ordinary differential equation, know how to get the solution. Those who do not know will learn soon. But let me write the solution. So, second order equation, there will be 2 equations. So, you can, the solution will be a cos omega naught t plus b sin omega naught t. So, where there will be a and b are constants, arbitrary constants we call it. So, it is a general solution. So, I want to give you an exercise here, this is nothing to do with the PD. So, I will keep on giving, you should do all when you learn this course. The solution can be written in the form, the solution can be written in the form you just do a bit of computations, you write the solution in the form. This is a better understanding in physics. You will get a better understanding with the this way of writing. You can write r cos omega naught t minus delta. You do the a bit of computation in the trigonometry. And what is r? R is nothing but square root of a square plus b square, and your delta is equal to tan inverse of b by a. Okay. This is called, this r is called the amplitude, and this is called the phase angle. You will see why it is important. You see, whenever there is a motions, you will see, and it is also a cos is and sine a periodic function. So, you see the solution is periodic, and the if you see that, if you look at this case, you see cos will take values between -1 and plus, and hence this y t oscillates between -r and plus r, and you see the Newton's first law obeys, it will never stop. The only thing is that this gives you phase angle. So, when t equal to 0, it starts from here. So, if there is no damping, you will have a problem with the system, you see. So, if you plot this curve y t, and it will oscillate. So, if you mark here -r and plus r, it may start with something somewhere. So, that is what is a phase it shows, it may not start with 1 or something. So, you will have a phase angle. It will go. So, you see it is a periodic motion and the oscillation the conclusion oscillation never stops, and that is what I expect, oscillation never stops, and as expected, that is what it says, because there is no damping and no external force. So, the moment if there is no external force acting on a system, the motion has to continue and you have your complete thing. So, let me do to the next one, case 2. So, you see, you from the solution you understood. Case 2, you are still taking the situation with f equal to 0, but c not equal to 0. You see. So, how does the equation look like? There is no external force. So, you have a system, no external force coming to the system, but then you are putting the damping, you are putting it in the oil for that particular example, or in other mechanical system you add damping. So, you will have this equation m into d square y by dt square plus c into dy by dt plus k y equal to 0. So, this is your equation, and let me write down again the solution I told you, you will know how to find the solution. So, let me write down the solution in different cases. It depends on various depending on there is what is called an auxiliary equation, and you look at the roots of this auxiliary. So, what is the auxiliary equation here? Auxiliary equation, that is equal to m into r square plus cr plus k equal to 0, and you have your solution r is equal to minus c plus or minus square root of c square minus 4mk by 2m. So, you have two roots r1 and r2. Okay. So, if c square minus 4mk is positive, you have two real roots, and when it is 0 there is a double root, and all of them you know. Accordingly, you can write down the solutions now. A e power r1t plus b e power r2t if c square minus 4mk is positive, and if it is a double root, again know how to find solutions, which we will see later. A and b are arbitrary constant, bt e power rt, because there is an if c square minus 4mk is equal to 0. When c square minus 4mk is equal to 0, when c square minus 4mk is equal to 0, you have this r is nothing but in this case r is equal to nothing but minus c by 2m. So, you have that, you see. And then the last case, when c square minus 4mk is negative, in that is a complex roots, in that case you can write down c is equal to your solution minus ct by 2m into a cos mu t plus b sin mu t. This is the case if c square minus 4mk is negative. And what is mu? If this is negative, you define your mu is equal to, in this case the mu is equal to square root of 4mk. So, that is positive minus c square by 2m, that is what you can write down that to solution, c square minus 4mk equal to 0. So, now the situation is different because c is always non-zero, in fact c is positive, that means this implies c is positive because damping is always non-negative. So, you have the case c is positive. Now, look at the first two cases, when the roots are 0, in these two cases, first two cases first case, within this first case means this situation, that means R1 is different from R2 and real, that is a situation. In that case it is a real, you can analyze this equation. If you analyze this equation, c square minus 4 m k is positive and hence this will be smaller than c. So, it will retain the sign of this one. That means in this case is actually R1 and R2 are negative. You can see that, because this is a, even though if you take plus, if it is minus no problem, both are minus, even if you take a plus it will be a quantity less than c, an absolute value, and hence this will retain the sign. When R1 and R2 are negative, look at these terms, e power R1t and e power R2t. R1 and R2 are negative, that means this will go to 0. So, you will have e power R1t, e power R2t goes to 0, that implies yt goes to 0, tends to 0. So, you have no problem. So, the case 2, this you know how to plot it. So, it's all vanishes, the solution. So, the moment you add some damping, the earlier when there is no damping, the solution were oscillating between minus r and plus r. The moment you add damping, the solution goes to 0. It may work in whatever, depending on the sign of a and b, whatever you take it in, initially it behaves the way whatever way it is, but eventually every solution decay in an exponential rate to the 0 level. And what about the case 2? Case 2 here, within this case 2, this is the situation. So, you have the case 2 situation, this is the thing I am analyzing it. In this case, c square minus 4 m k is equal to 0. So, your yt is has a term, the first term no problem, a into this one again will go to 0. The second term, there is a term e power rt. R is negative, there is no problem, even here R is negative, because R is nothing but minus 2 by m, but here is a term which goes to infinity, and here is a term which goes to, there is a term which goes to infinity, here is a term which goes to 0. So, there is an indeterminate form, but let me give you another exercise. You have to keep on doing this exercise. This is a nice exercise, a small exercise from your analysis. Show that t e power rt goes to 0 as t tends to infinity. You see. So, I have a nice exercise against the solution decay. So, both these cases, case 1 and case 2, the solution decays and there is no oscillation. So, when you add damping, damping is when this will become 0, suppose m and r fixed, for a particular system m is fixed, k is fixed, and the sign of this is determined based on how much damping you add. So, if you add sufficient damping, 4 m k is a positive quantity, and if you add sufficient damping in such a way that c square is greater than or equal to 4 m k, there is no oscillation, phenomena, and the oscillation goes to 0. So, these two cases are called over damped system. So, you are giving so much damping so that the entire over damped system. So, you have added so much damping so that complete oscillation has vanished and the solution goes to 0 exponentially. But now to the third case is this situation. When you look at that term, this is a cosine term, this is a sine term, both are bounded. So, the cosine and hence this entire term is a bounded quantity. but this term is a quantity which to 0. So, let me take to the third case. So, case c square minus 4 m k is negative. In this case your solution y t is equal to e power minus c t by 2 m into a cos mu t plus b sin mu t. What I said is that this is a bounded quantity, bounded, and this term goes to 0. So, y t still goes to 0, and this is a situation you have damping, but then damping is not too much. So, this is called the underdamped system. Damping is there, but underdamped system. So, you see all this when there is no damping, complete oscillations, oscillation does not decay. So, these two quantities shows that there are still oscillations. So, this will oscillate between some quantity. So, let me write down the solution in the another form. The other form you can understand this oscillation much better way. So, that is what I say, you can rewrite this equation in another form, minus c t by 2 m into cos of mu t minus delta. So, you see it is a solution. So, this shows the oscillation is not removed completely, but then there is an amplitude, and that amplitude basically goes to 0. So, it oscillates, but eventually goes to 0. So, if you plot the graph of this function, it oscillates, cos takes value between minus 1 and plus 1, and hence it will also takes the value between these things. So, if you have this if you plot this curve, this is an exponentially decaying curve with r. So, if you plot that curve, you will have a curve which goes to here. This is nothing but minus r e power minus r, I think, and this, yeah, minus r, and here you have a plus r, and you have a this curve. It is a symmetric curve. So, the it does not look symmetric, but it is a you can plot it. So, this is the curve minus r e power minus c t by 2 m, and this is the curve r e power c t by minus c t by 2 m, and it oscillates. So, it starts here, it will go, and maximum it will go. So, it will oscillate something like that. So, you see like that it will go. So, you have this complete analysis in the, this is a case 2. Okay. All right. So, what do you, so the what is so far we have concluded, you have a system, there is no external force, we have considered only two cases. The case 1 with an no external force, no damping, full oscillation, so oscillation continues in the same pattern. When there are no external force, but then there is a damping, it depends on how much damping you give, either you can kill the entire oscillations, or the oscillations will be, if the damping is less, the oscillation retains, and then you have but it still goes to 0, and that is it. So, the moment you have damping, eventually the solution goes to 0. Now, let me go to the next case, where you have the situation thing, you have the case where you have force F not equal to 0, but you take C equal to 0. No, so we analyze the case when F equal to 0, both C equal to 0, C not equal to 0, and now we are trying to analyze the case when there is an external trouble or external advantage. We do not know the external force is advantageous or external forces. In mechanical system, quite often the external disturbance is advantageous, but we will make a remark that the same external force is advantageous in the electrical circuits. So, the interpretations will be different. So, we are trying to think in the setup of mechanical system. So, this is nothing. So, it is a forced but undamped system. So, there is no damping, what will happen is that one. So, this is so maybe I will this is a more difficult case. So, let me do the difficult case little later. So, let me do first because when already seen that when C equal to 0, when F equal to 0, there is vibrations, but now there is an external force coming into picture and still there is no damping, you expect more trouble in the mechanical systems. So, let me do the easier case first and then we will go to the other case. This is a standard case. So, when at F equal to 0, how do you write down the solution? So, you may not be able to write down the solutions with the general F, because it is a non-homogeneous second order equation. So, first you have to solve the homogeneous linear equation and then with certain right hand side you will be able to write down the explicit solution. So, you have to find what are called particular solutions which you will study later. So, but certain F you will be able to study, obtain the explicit solution. So, we will assume F is of the form with a single frequency coming and external force coming F naught into cos omega t. So, this is F t where F naught is a constant, this is a constant and then omega is the frequency coming from the external one. Omega naught is the corresponding frequency corresponding to your mechanical system. Okay. So, I can write down. So, already as I told you, to write down the solution y t, you need a solution of homogeneous equation which you know already, homogeneous equation plus one particular solution. You will understand this more when you study the second order particular solution. And let me write down the solution completely. How to do it you will learn later. So, let me write down the homogeneous solution which you already seen. Whatever I have written down is the homogeneous solution plus you will have a particular solution. The particular solution let me denote it by ypt. And what is a particular solution ypt? Let can write down the particular solution. I have something F naught, this is cos of omega t minus delta, omega t minus delta by is a complicated, little complicated, but you can see that omega square whole square plus c square omega square power whole power half. I hope the computation is correct. Anyway, you should do that. Where delta you can also write down, delta here is c by k m omega square. So, you see you can exactly calculate your phase coming using your external force here. So, there is nothing specific in this case. The moment you have damping it should work. When there is no damping this term was not no, when there is no external force this term was not there due to the, but this was there. This is without a homogeneous solution, that means it is a solution with F equal to 0. You understand the behavior. So, that behavior will be retained and plus you have an extra term here and the extra term also have. So, there is no additional feature here. The only additional thing is that, so the behavior everything more or less is a similar thing, and we have seen that in all cases with F equal to 0, with F equal to 0 you have seen that the solution goes to 0. So, this is a term phi t which goes to 0, this will oscillate. So, what will happen is that y t eventually will go to this particular solution ypt. Yp, no, let me not write, it will go to 0, it will behave like ypt. So, you can understand the behavior of ypt and so that. So, as t tends to infinity. So, the behavior at large time yp will be of ypt which is coming due to the external force and nothing more interesting. So, this is called the steady state. This yp, if physicists call this is the steady state solution. You can understand why it is called a steady state, because eventually steady state, and this phi, the solution to the homogeneous system, is called the transient state. Transient state. You can understand these terminologies very well. It matches because in the beginning of the time, initial time, you will have the contribution as a transient state, and eventually the transient state will go to 0 and the entire solution will behave like a steady state solution. So, now we come to the last part, next case, the more interesting and difficult case. This is the case where f not equal to 0, but c equal to 0. You see, there is no damping, external force is there, external force, but no damping. You see, why damping is important, you will see here, whether it is any system. So, that is, it is the forced undamped vibrations. This is the situation. So, let me here itself there are two cases. So, to study separately two cases now. You can see. So, you have to split because it is a complicated thing, two cases behaves differently. So, what is your f? F I am again assuming to of the form f naught into something like cos omega t. I am writing this one. So, what are the in this case? First let me tell you the sub case with that one. This is called, you understand why, without resonance. I am going to introduce a new terminology, without resonance. That means you have a natural frequency omega naught coming from the system, and you have an external frequency coming from the external force. So, the without resonance is the case, the external frequency is different from the natural frequency. So, omega naught is different from the frequency coming here. Then this is not the most interesting case, you can just write down the solution yt. You have a solution of the homogeneous system. This will look like a into cos omega naught t plus b sin omega naught t, very easy. So, this is the solution corresponding to your homogeneous part, and then there will be a particular solution. It may look like f naught into m into omega naught square minus omega square into cos omega t. So, you see, you will see that when omega not equal to omega, this is not the particular solution. The particular solution can have problem, and why that problems mathematically you will understand when you solve second order linear equations with constant coefficient, which we are going to do it anyway in future. But you see that immediately trouble, we cannot write this equation is clear from here. So, this is again a natural thing. So, when you have c equal to 0, you have your normal vibrations, it is happening because then there is no damping, naturally that full vibrations will be there, plus you have a term here and it will vibrate as it is. So, this is the case which you have, there is nothing new whatever we have discussed. The another interesting case is with resonance. Why call it with resonance? This is the case when omega not equal to omega. This means you have a natural frequency to your mechanical system, and external force is coming with the same frequency. When these things are there, to solve this equation, the finding the solution and writing the solution is in a different way. And let me again write down the solution here. Just write down the solution. So, the equation in this case looks like this: dy by dt plus omega naught square y is equal to f naught by m cos omega naught t. You see, you already seen that cos omega naught t is a solution to this one. So, whenever you want to solve an equation, if you want to find a solution to this one, anything like cos omega t may not work like a particular solution. Cos omega naught t is a solution to your homogeneous equation. So, the solution is slightly, you have to write it in a entirely different way. The solution, let me write again here, the solution will look like this: yt is equal to a cos omega naught t plus b sin omega naught t plus this is the difference here. Now, how things behave: 2m omega naught into t sin omega naught t. So, the behavior of this term is fine, it oscillates between a and b. If you write it r e power, you already seen that it will oscillate between full a. But look at this term, this oscillate, this sine part oscillates, the sine part oscillates between -1 and 1, but you see as t increases, this increases to infinity. So, what happens is that even though this oscillates, if this term, this such a term, such an unbounded term, as time goes the amplitude is increasing. That is what happens when t becomes bigger and bigger, the amplitude is increasing like that. So, it will start from here, the amplitude increases, that means the vibrations become unbounded. So, if you plot this curve here, the curve may, you can look like that. As time goes, you see it goes to become bigger and bigger. So, you have a mechanical system, you are meeting with an accident or something, some vibrations coming in your motorbike or something, and the vibrations comes into you, that and the person who is riding the thing, you do not want the vibrations to on you. But here if this is the situation, an external frequency comes with that one, and these vibrations becomes larger and larger, and you are going to have, meet catastrophes. And this is what, when you design any mechanical system like a bridge or anything, you have to take into account in such a way that you have to put enough damping in the system in such a way that the external frequency, it may not be, the external frequency may not be due to your under your control. For example, there will be lot of vehicles traveling through your bridge. So, when you are vehicles traveling through the bridge, it will create automatically its own external frequency, and your system will have a certain frequency. So, if your bridge or whatever it is do not have the frequency, the damping enough, and it is possible that the frequency of your bridge may coincide with the external frequency coming, and the bridge will start oscillating and bridge will collapse. This is the famous, you should go and read the famous Tacoma bridge collapse. Tacoma bridge collapse. This is probably happened in 1940s or something. This is a famous bridge in USA, where what happens is that in the early morning the bridge starts vibrating with smaller and smaller vibrations. By the time it, and the vibration became bigger and bigger, and by the time it 11 o'clock or something, the vibrations were so big, so the amplitude was so huge, and the bridge got collapsed. The interesting tale of that one is that nobody died in that huge disaster except a dog. And this is also the reason, probably you have seen that in the military or army marching, in the cadence marching through the bridge, the army march not like what we walk, we create different types of vibration, but the army marching will be with a particular frequency and it will be very high. That is why when the army marches through the bridge, they will not allow the continuous marching of the army. They will break into small pieces, a small set of people will cross the bridge, and then only the other seat will. So, they will break, because they do not want to create a frequency from the external side which matches with this one. So, as this example, before going to quickly I will not go into quickly the other examples, I will just explain few examples which you will see details in future other lectures in the later part of this course, but I will explain few important examples. Before going to that one, when you analyze this same system in the electrical circuit, the analysis is the same, you look at it, but the interpretations are now different. Where here exactly what is undesirable in a mechanical system is used to good use in electrical circuits, because what will happen is that when you want to tune a radio or TV, what you are doing is that you are setting a frequency, natural frequency to the system. So, when you are saying changing your channels or changing the radios, when you are changing the frequency means you are changing the frequency of natural frequency of the system, and externally all that telecasting all the channels with the different frequencies. What you are doing, trying to do is that you are trying to put a resonance situation in such a way that when you are setting a particular frequency to your natural frequency to your system, there will be all the frequencies around your radio or TV. It will only match one of the frequencies of the particular channel or a particular broadcasting thing. When these two matches, these two will create a resonance, and hence that is what is called an amplifying. So, basically a situation of resonance are happening, even though whatever coming is very little, it matches and then it amplifies, and that is why you get a particular channel. So, you see the same thing, the interpretations are different, but you have to analyze it coming from the same equation, entirely two different fundamental problems from two fundamental areas of engineering. Okay. So, this much details I will not do it anymore. In the next 10 minutes or something, I do not know how many examples I can do it. Anyway, I am not going to do too many examples. I will be writing down few interesting, I already wrote down one equation, it is called the pre-predator model, called a Lotka-Volterra model, and another equation you will be studying here in later is called the Duffing equation. Duffing equation. The equation looks like this: x double dot minus alpha x plus beta x cube plus delta x dot, and you can also have the driving force if you want. So, that you have a homogeneous equation. This is non-linear, due to this is non-linear, and you have the, you can put something like gamma cos omega t if you want a driving force, external driving force. You see. Of course, if this beta and delta are 0, is nothing but this part is the linear part. Of course, this is also linear, but the linear, simple linear oscillator. So, you can think it as the perturbed model of the linear thing, perturbed model if you want to see. And alpha is if you want something thing, alpha is nothing but your stiffness if you want it in a mechanical model, stiffness, you can interpret that one, and beta may be the amplitude, and delta whatever it is the damping. So, this is something a similar thing. If you look at your mechanical model, it is a similar thing. So, you have this term, similar terms, only this is a more term, this is the damping, if you can see that one. This model was probably introduced by George Duffing. As I said, if you want to understand more, if you want a linear system, you will be restricted to only thing. If you want more general understanding of your system, you have to have your components, the nonlinear perturbations and perturbations, and this is the thing. So, you may see so for example, your stiffness of the spring may not obey the Hooke's law exactly, and such kind of things. It will not follow precisely the things like that. So you will see this equation and probably more about the derivation, not too much, but we are going to study this equation in detail in our future lectures. You can write down this as a system, you will see that also. You can write down this as a system with x dot is equal to y. It's easy to write when you have an x dot is equal to y, you have your y dot is equal to, you put that all the alpha x minus beta x cube plus minus delta y. So you see you can write this as a system. So you have a very beautiful equation. As I said that a reasonable extensive study will be done here at the end of it, and this is one of the model which we want to understand it in the qualitative analysis. So to understand or if you want to know how these equations are derived, you can get into the references which we have given, or you can also search through internet if you want to understand more. Very one of the all right. So another model which you may see is called the van der Pol equation. So it is a van der Pol equation. These are all oscillatory equation. Earlier it was an electrical mechanical model. This is also an interesting model coming from electrical circuits. Is again call it oscillator, you can also call it oscillator. Everything is that form, x square minus 1 into x dot plus x. Here also if you want can put it 0, or you can also put it something an external term a sin omega t if you want a forced. So this is called the unforced van der Pol equation. So this you can call it forced water. So you are putting a force, external force there. You can write down this again as a, there are different ways possibly you can. So when I am writing it as a system, it does not mean that it is a unique way of writing it. You can write down the systems in different ways. So what I have done here is the easiest way of writing it, and different ways of writing it will have different effects, plus mu into x square minus 1 into x dot. This is known by the Dutch, van der Pol was a Dutch engineer, van der Pol, and introduced in 1927 when he was working in the Philips company. That is the time he introduced. But it also seems that this equation is derived a little earlier than van der Pol due to Rayleigh, Lord Rayleigh, but somehow it is not in that name. It is introduced probably 1896 itself, 30 years before that one. But it is he is the one, at least van der Pol is the one who extensively studied this thing. So you will see the behavior probably in this, and in this study in our course you will see the chaotic behavior, probably periodic solutions and chaotic behavior, all that analysis probably you will see that. There is also further equation, other people like Cartwright, I think I am right, Cartwright and Littlewood. They are further whole mathematical study later, more detailed mathematical study. Here it is some engineer, he is more like a done like some mathematics theoretically and experimentally, a complete study, more detailed mathematical analysis probably a little later by these people. So you will see about this type of equations also in our this course, you are going to see that. Of course, one of the easiest this equation, one more thing, these equations have not only application in this kind of thing, it also has applications in biological science. That is so as I told you, as you already seen, the same equation may have different effects in different things, just like the second order equation which we have derived and analyzed comes from a mechanical system, it also comes from the thing. So, here in the study of the neurons, the action potential of neurons, the same equations have extensively studied and its chaotic behavior. It is also seismology is used where you want to understand the geological flow, two plates. So, this same equations has applications in other areas also. So, when you study, so what you will be seeing here, our concentration is not to a particular problem, but our concentration will be how these equations behave. So, our analysis is going to be the qualitative analysis of this general equation. Interpretations has to be done according to your problem, according to your physical problem. The other equation, of course, this would have been come here, basically the pendulum equation. Pendulum equation, this you also may see a pendulum equation, and this looks like this more complicated. Let me write it in a slightly general way, plus BL theta dot plus mg sin theta equal. It's a standard pendulum. You have a string, at least length of the string and mass is attached. All of you know that one. Those who have gone through your +1 +2 lecture class, and how the pendulum swings. So, okay. So, this is the force due to friction. Force due to friction. The term. This is something like looks like a damping part. So, if this term is not there, and if you write it in a simple form, say ml theta dot plus mg sin theta, this is basically an ideal model, okay, more of an ideal model. So, you will see these things, ideal model, and which we are going to study here, whatever it, okay. And the other case, when you study B positive, so there is that is a more general case where there is a force due to friction. So, let me more or less finish by writing to you one more equation, which is the probably the first the chaotic behavior is observed in the Lorentz system. I will write down the system. So, you can, why I am writing this system is that by the time you come to the end of this course, you should be familiar with the system, so that you will understand its behavior, the qualitative analysis in a much better way. So, if you go through this one, do a little more study on these systems, how these systems are coming, and then you understand. So, let me just write down the thing, I will not again tell much about it. This is minus sigma x plus sigma y, and then y dot is equal to Rx minus y minus xz, and z dot is equal to minus bz. This is again extensively studied to understand the chaotic behavior. Chaotic behavior. And yeah, this is actually developed in the study of meteorological problem with of weather prediction, and you will see again a little bit analysis of these problems in future. So, there are some other interesting model, we are not sure about, we will be able to cover all these models, because then our one semester course may not be good enough to cover that one. For example, some nice models, if we get time, I am not a thing for satellite motion, so important, right, satellite motion, examples from satellite motion. So, it's typically you have a satellite, so you have a typically a satellite, so you have a satellite is in this position P with xy as the coordinate system, xy, and then you have this has the thrusting capacity. So, you have the radial thrust if you want u1, and you will also have a tangential thrust u2. So, you can derive, so the modeling is much easier here. So, you can easily model these equations. So, the modeling is not the important thing. In the satellite thing, in addition to model, you have to also give a kind of study the control problems. So, if I want to write down the equation, the equations may look like this: mx dot is equal to f of x and y dot is equal to f of y. So, this looks easier model, but then since this satellites a better model, better way of writing is not in the Cartesian coordinate system, in the polar coordinates. Writing in polar coordinates is much more better. So, you can do the very simple analysis, you do not need much things to be done. So, let me just write down the equation. So, it will be have something like that radial. So, you have r and theta. So, you can write down the radial and so you can do very simple analysis, not too much complicated. If we have time we could have done it, but we will not do it. I am not sure we will be able to do a much better analysis also in this problem. But let me write down for your familiarity, this equation can be converted with very simple analysis to the equation of the system of 2 second order equations. So, let me do that one, r theta dot square equal to minus k by some r square, and m theta dot double dot plus 2, again it is a nonlinear system, theta dot m 2m into equal to 0. So, you see, so you have eventually, so analysis for this kind of things is better to do it in polar coordinates, not in our Cartesian coordinate. So, this is a system of 2 equations, a system of 2 equations, second order system, that is what it is. So, it is not a first order system. So, when you go convert into a first order system, it will be a system of 4 equations in 4 unknowns, and there are plenty of other examples where you can study and it is available, and with this we will complete the module 1 giving examples, in the next module we will be giving the preliminaries. We will give some preliminaries in the case of linear algebra, we will also present some preliminaries of analysis, we will just do it which we require for our course. And so, thank you very much.